Usually, it's not. Usually you do everything you can to remove redundancy. But there are situations where redundancy helps you. If you have a redundant expansion of a signal, it is less affected by noise, often, not always. But often noise is less of a problem with a redundant system. And so if you have a problem with round-off noise or signal noise, sometimes a redundant system using frames rather than basic functions has some advantage. Of course, you lose the compression. The whole idea of compression is to remove redundancy and for sort of working in the opposite direction. But in the case of denoising, sometimes redundancy is desirable. All right, let me move on. What's our time looking like?
15 minutes?
Okay.
Oh, can I have questions?
Let me go to, let's take a look at this particular example. In the upper left-hand picture, we have a chirp signal. This is a signal whose frequency is changing and whose amplitude is changing simultaneously. So in the upper left-hand corner, you have that. In the upper right-hand corner, we have added noise to it. Now, if you try to filter that with Fourier analysis, it's a mess. It gives very poor results. So using traditional wavelet analysis, you get the lower left-hand corner. Using a redundant wavelet decomposition, in the lower right-hand corner, you've done an amazing job of removing the noise without distorting the signal. So both the frequency change and the amplitude change is recovered, and virtually all of the noise is gone. And that's a place where the redundancy helps you in the denoising. It hurts you in terms of compression, but it helps you in terms of denoising. Let me stop just for a moment and make sure you understand this, this idea of denoising. If I have a signal, and if I can compress that signal into a few coefficients, from Parseval's theorem, it tells you that those coefficients can be large. I have my signal, it has a certain amount of energy. I put it into the wavelet system. Most of these coefficients or some of the coefficients are very large. I take the others and throw them away. Just cut them off. I run into a threshold and remove them, set them to zero. If the noise is with the signal, the noise will have its energy uniformly distributed over all the coefficients. I would assume the type of noise it does so. So all of the noise energy is quite small, again from Parseval's theorem. So the small noise and the large signal in the wavelet domain. The time domain wasn't that way. In the wavelet domain, we made the signal get bigger and the noise get smaller. Then we just cut the small stuff off. We threshold and make all the small stuff zero. Then when we reconstruct the signal looks amazingly good and the noise is gone. I don't mean the noise is small, I mean it's gone. You can't see it. It's amazingly good, and this is what is happening in this particular example here. Another example of the same phenomenon. This is the skyline of Houston, the city where I'm from. And so I took this upper left-hand picture and used that as a signal, added noise to it, and used the two different methods of denoising. And the lower right-hand corner, okay, some of the noise did creep through, but most of it is gone. What are some of the applications? Well, right now, one-dimensional wavelet theory is fairly mature. It's fairly finished. It's understood. There's not a lot of need. Multi-dimensional wavelet analysis is still a pretty active research area. So image processing, multi-dimensional signal processing is still developing in the wavelet world. But you find a whole variety of applications that have found use in a few years ago, and he was using a wavelet system to model economic pricing. And I just was astonished. I was expecting some communication or some seismic or something, but he was modeling the price of oil or something. I don't know what.
Did he make $1 million?
Pardon?
Did he make $1 million?
He wouldn't tell me what his details were. I thought it was interesting. If it had been a technical person, yes, but an economic person, no.
What is noise in his picture?
Pardon?
What is noise in his picture?
What is the noise? It is a signal. In his economic, is a student.
I think he was using it not for noise or compression, but using it more to look for trends and to see if he could find components that can carry more information, and so he could predict the future prices. And of course, if you can predict the future prices, that you can use that to advantage. The only problem is if you can predict the future prices and then you do something with that, it destroys the prediction. But many people do it. Okay, I think that's what I wanted to say about the application. What do I think is happening with wavelets? One is I think they are a standard tool, and that in the past, query analysis is taught to undergraduates, and wavelet might be taught to graduate students. More and more, we're discovering wavelets being taught to students who are still undergraduates. Special wavelet systems are being developed that fit a particular application better than the original wavelets did. The use of wavelets for speech analysis, we thought that was going to be terrific. And it turned out it hasn't worked out as well as people had hoped. It seems that signals which are multidimensional have more redundancy, and they are better suited to wavelet analysis than low-dimensional signals that have less redundancy. So perhaps more with images than with just one-dimensional signals. A variety of other applications will be coming along, I'm sure. Here are some of the references, and there are many, many research papers. These are just some books, and the book, of course, that I'm most fond of all is the last one, because I wrote it. And so it's developed exactly the way I would do it. Thank you.
First, I want to say that wavelets is rather difficult to understand. I myself don't understand about wavelets very much yet. But I can see that it is rather interesting and is widely and have wide application. And I really want to learn about wavelets. But I can see that is very, very difficult. So could you help me how to start, how to get things started studying with wavelets?
That is hard to answer. But let me tell you that there's another way to think about this, and that is to understand wavelets. You don't have to do calculus. There are no derivatives. There are no integrals. Everything is done in terms of sums and finite sums. So it's possible to work with wavelets and not even understand calculus. I'm stretching it a little bit. But in some ways, because